So yeah, so God help us. Yeah, let's see. So we're going over stacks, queues, and decks. But last week we went over arrays and stuff. One thing, first I wanted to keep in mind is that data structures are independent of programming language, right? So like if I have, let's say, a stack, right? Python, a stack is, think of it as an abstract thing. What do I mean by abstract thing? It means it's an abstract data type. What you can think of that is this, that there's a data structure, right? Think of it as there's a data structure. Let's assume there's a data structure, and we have imposed some properties on it, right? We've imposed some properties on it, and those properties, right, have made it special in a way, right? So if you have a data structure that strictly obeys those properties, right, it becomes let's say like if you have a primitive or if you have some structure or some type and it strictly obeys those properties, we call it a data structure. Think of it that way. What that means is this, that these data structures under the hood are implemented using already existing stuff. For instance, if this doesn't make sense to you, let's use the stack for instance. So in Python, the stack is implemented using a list, right? It's implemented using a list. That means that I can take a regular list and then impose on it some restrictions. And if that list always obeys those restrictions, I can call it a stack, right? In other programming languages, the stack won't be implemented using a normal Python list. They can use a linked list, right? So then you realize that the stack is kind of like, so let's assume this is that underlying data structure. A stack is more of like something like this. It's more of like an interface, kind of an abstract thing. Under the hood, somebody may use a list. Under the hood, somebody may use a linked list, and so on and so forth. That's why we want you to understand the data structure kind of like as an idea, as a concept, right? And not restrict it to implementation, right? Or not to even restrict it to a programming language. Today, one of the questions you look at, you realize you see something like implementing a queue using a stack, implementing a stack using a queue, and so on and so forth, right? So there's a data structure. Its implementation can vary across programming languages. Its implementation can even vary in a particular programming language, right? So those are data structures. So a stack is not strictly a list. If I come to Python, you can say that, oh, I can implement a stack using a list. Can you people see the difference? Like the implementation can vary. There's no fixed implementation of some fixed data structure. Does that make sense? That was a lot of words, but does it make sense?
Yeah, it does.
Yeah. So the stack is a data structure. And it's an abstract, people call abstract data type. What that simply means is this, that hey, it is kind of, I can take a regular data type here, then I can impose on it some restrictions, some properties, right? And whenever something, that data type always obeys those properties, then I can call it a stack, right? That is simply what it means. That the implementation under the hood, how we implement it can be very different, right? It can vary across different programming languages and so on and so forth. So based on that, let's go on to the next thing I want to talk about. So in Python, which we usually use, we can just simply implement a stack using a Python list, right? Why? Why can we easily use a Python list? Well, forget about how you can implement it. Think about what a stack is. A stack is a data structure. So think of it as a container. A stack is just a container that allows you to add an item, right? Add an item to the top. I'm saying to the top because right now I want you to think of a container like this. Like when we're in GHS and there's a table there, right? And when you put your books on the table, right? So think of it as a container. And then to add an item to the top, that means that when I bring an item here, I'm going to put the item. So here it is empty, right? Here it is empty. So I can put an item. Let's even use like a table. I think that'll make it clearer. So think of it as your table, right? Let's assume this is your table, right? And this is our stack. Our stack is basically a table. I said the implementation can be anything, right? Care about the concept. The stack is a data structure that allows you to add an item. So if I bring an item, I have to add it to the top here, right? If I bring another item, I'm going to add it to the top here. Another item, I'm going to add it to the top here. That is one property of a stack. The next property is this, that if I ever want to remove an item, I can only remove from the top. Remove from the top. Remove from the top. So that means that if I want to remove an item right now from this stack, what I can remove is this guy. This is the only guy I can remove, right? If I want to look at an item, I can only look at the item at the top. So we call it peek. Peek at the top. Peek at the top. And all these things should be done in constant time, O of 1. Constant time, O of 1. So if you can design a data structure that strictly obeys these three properties, which we are focusing on now, it is a stack. I don't care how you implement it, whether you're going to use a list under the hood, whether you're going to use a linked list under the hood, whether you're going to use whatever data structure under the hood. So far as it implements this, you can confidently call it a stack. Does that make sense? So that is just what a stack is. And we know that, oh, so in Python, if I come to Python, I'm like, oh, a list can actually help me do this, right? A list can help me achieve these three things. Then I can implement a stack using a list, right? Because if I have a Python list like this, if I want to add an item at the end and I do dot append, that's O of 1, right? That means I add the item here. If I want to remove an item, I do dot pop. That also removes the last item. That is also O of 1. If I want to look at the last item, Python can do index -1. That also gives me the last item. Therefore, I can implement a stack using a list. Somebody too can use a linked list, which we'll look at later, and so on and so forth. Just what I want you to keep in mind. Now go to a queue. So the best picture to put of a stack for you is like you have a table, you put items on it, you put items on it. There's something I didn't want to mention, but let me mention it. Why? When you read different books, right? They are like, sometimes they are like add to the top, other times they are like add to the bottom, they are like add to the back. When the book uses a top, you can add it only to the top of the stack. They mean this, they're using this illustration. When they say add to the back, they use an illustration where it is like this. Like the first item you add comes here. The second item you add comes here. Third item you add comes here, right? Because they're using like the list illustration, right? Because when you remove from a list, it's just like this, right? The next thing I wanted to mention is why I wanted to focus on time complexity a bit. Why is removing from a list? We'll be focused on this because that's the programming language we use here. Why is removing from a list constant time? Now, if you take a regular list like this, 1, 2, 3, this is something we discussed last year, so let me just rush through it. 1, 2, 3, 4, 5. Now, if you want to remove something from this list, right, look here. How are lists represented in Python? If you went through last week's series, we said that this is how it is done. Every item in the list has indices, right? 0, 2, 3, 0, 1, 2, 3, 4. And the indices in the list are strictly necessary. We care about them, right? Lists are indexed. That is why if this is my list, I can just do list index 0 and I get 1, right? So lists care about the indices. Because they care about the indices, what happens is that they are stored in a contiguous block of memory. If you watched last week's video, you'd know all these. So let's say if you go into the memory, if I want to set a list of 5 items like this, I go look for some 5, chunks of my memory. So your memory is something like, think of your memory as some table, right? Like this, this. A part of it may be occupied and so on. But if you want to store this list, you go and look for some 5 contiguous, block of memory. And then you store your items in it, right? So that means that all your computer needs to do is that it needs to just remember the position of the first item, the memory address, the address where it is. And then because they're all contiguous, it can easily jump around. That's why when you do list index 2, list index, everything is constant time. It's constant because because it knows index 0, the address of index 0, if I want index 2, which is this guy, right, it can simply do 2 plus 0, right? Just do arithmetic, just add, some memory addition, pointer addition is just addition, it's very simple for the computer. Then to just jump here, and that makes it constant time, right? So that is why indexing is constant time. List index, anything, index k is constant time, right? Now let's go removal. When you remove an item from the list, look at something here. Let's say I want to remove, let's change this color to green. Let's say I want to remove 1. Now, we've already established that indices are very important to the list, right? Like when you remove an item, when you add an item, it still needs to maintain the indices, right? So if I remove this 1 right now, the new list that will be formed will be 2, 3, 4, 5. Now, indices have to be maintained. So 2 becomes the new index 0, index 1, index 2, index 3. So if you look, that means that they have been shifted forward, right? Python shifts them forward. Now let's look at the work done in shifting them forward. That is what we call time complexity. Time complexity simply means the work you do, right? The effort you put into doing something, right? So here, I removed just one thing, right? I just removed this 1. But look at how many items I ended up shifting. I ended up shifting 2, 3, 4, 5. I literally shifted everything after the 1. Generally, I shifted everything, right? And because I shifted everything, the work I did is proportional to everything that is in the list. How many items are in the list? N items. Therefore, the work I did is O of n. That is linear time. So when you remove from the start of a list, the time complexity is O of n, it's linear time. Why? Because you have to shift everything so that you can restore the indices order, the arrangement order. Because if I remove this one here, I can't omit index 0. Lists always have to start from index 0. So that is how it works. Someone will be like, what if I remove from the middle? If you remove from the middle, the work done is, we're going to shift, let's say, n over 2 items, right? If I remove from the middle, let's say I split it exactly here. that is becoming a bit messy. Let's say specifically here. Let's say I remove 3. If I remove 3, I don't need to shift 1 and 2 because they are still index 0, index 1. But I need to shift 4 and 5 forward, right? So the work done is like I shift half of the items, n over 2. But we know that in time complexity, we drop the constants like this, right? So it's actually O of n over 2, but we drop the constant and then it becomes O of n, right? So that's how it works. Now, the only part where it is constant time is if I remove from the end. That is the dot pop. Dot pop. Now, if I remove from the end, look at this. If I have 1, 2, 3, 4, 5. If I remove from the end, I don't shift any guy, right? Like if I remove from the end, I just cross this guy out. The indices are maintained. I don't remove from any parts. So this is constant time. So pop is constant time. Remove from the end. That is why when we are implementing the stack with the list, to remove from the start, right? When you want to implement this functionality, remove from the top or remove from the start, right? We just use a dot pop. And because that's constant, that gives us the constant time that the stack needs. Similarly, append is the same thing, which you can realize by now. If I want to add an item to a list, right? If I add an item to the front, let's assume this is your list. 1, 2, 3. If you add 4, if you add an item to this list, if you come and insert it here, let's say you come and insert 6 here. Before you inserted the 6, this was index 0, index 1, index 2, index 3. When you insert the 6, we need to shift these guys backward, right? You need to shift them backward so that 6 will now become the first index 1, then this will become index 2, index 3, and index 4. Shifting everything backward is O of n, and so on. But if I add an item to the back, 1, 2, 3, 4. If I just add the 5 to the back, I don't shift any guy. So that becomes constant time. I don't, I just do one thing. I just append it. I just join it, then I'm done, right? So appending to a list is constant time. That is why we use dot append when we are pushing to a stack. So that is also O of 1. That is basically how it works. Peak, Python peak, as we said indices, right? It's easy for you to look at indices and so on and so forth. So that is how the time complexity is calculated for a stack. You can extend the same things for a queue. Actually, let me talk about the queue one. The queue is a bit tricky in Python. Now, look at something here. I know some of you are doing something like this. You're like, oh, let's create a queue. Let's call it queue. It's equal to the empty list. Okay, add to a queue. What does a queue do? Well, if I'm adding to a queue, well, how do you put add to a queue? How do you add to a queue? If I'm using a list, how will I add to a queue? A queue is a bit tricky.
You append it.
Okay, if you append, let's say we use append to add to a queue. But let's look at how a queue looks like. A queue is like, think of the queue as this. This is how I think of the queue. As if we're going to a dining hall, right? We're going to a dining hall. If you come first, not think of the Ghana High School dining hall. That one we don't respect who came first. I mean, let's in school like Upoko or a school where there are the Catholic priest standing there and God of War. Then we respect the queue. But generally, we don't respect the queue. But let's assume you are in an IS school, like Upoko or a school, where we respect the queue. Once again, the first person who came first in the queue will leave first, right? So the queue is like, if you entered first, you have to leave first. If you entered second, you have to leave second. If you entered third, you leave third. That's how a queue works. So let's say I want to add the numbers 1, 3, 5, and 7. So I first join 1, right? I first put 1 because 1 wanted to enter first. Then I do a queue dot append 2 and so on. So now my queue looks something like this: 1, 3, 5, and 7. Now, how do I remove? When I want to remove from the queue, which item can I remove? What can I remove?
You remove 1.
1, strictly 1, right? Because those are, as we said, it is a data, they have their properties. That's a data structure. You must stick by that property, right? So you can only remove 1. How will I remove this 1? How can I remove this 1? It's a Python list. How can I remove 1?
Pop 0.
Pop 0, right? So I can do q.pop 0. What is the time complexity of this? Yeah, pop can take, if you just do .pop, it remove the last item. If you pass an index to pop, it remove the item at that index, at index k. But
Yeah, I meant like pop left.
Pop left, okay. So you can use pop left, but pop left can't work on a list, right? So pop 0, so look, you do a pop 0 here, you do a pop 0 here, but this pop 0 is similar to what we discussed here. You have a list and removing the first item. What work do you do? O of n. That means, but key wants to do it in O of 1, constant time. That means you can't just implement a queue using a Python list, because pop 0, if you pop 0, is O of n. Why? The fact that you called it a queue does not make it a queue. That's what you should know. What matters is how you implemented it under the hood. Under the hood, you use the Python list. When you move at index 0 of a Python list, right? When the length of the list is not 1, right? Then the work done is going to be O of n. So if you want to do a queue in Python, what you do is you can actually import it, right? You can actually import it. How do we import it? Generally, we use the deck, right? A doubly ended queue. In Python, that's something like Python is so cool. If you're solving any coding problem or why you think I'm going to need a queue, I think it's from collection. You can just do from, is it from collections? From collections, import deck. And this is how this works. It's been so long I use this guy. So if I want to create a queue in Python, I just do this. Then like, so my queue is equal to, if this is even a cool thing you can do. Let's assume you already have this list. You already have this list. Um, where's this list? Let's see. Let's say you want to create a queue. Just do queue is equal to your deck of this. Then if you want to add, you can simply append dot append, like so. If you want to pop, as Fernandez said, you can just do queue dot pop left, and then you're done. This pop left is going to be O of 1, going to be constant time. Why? Because those people who implemented this thing for you in Python, they have implemented it so efficiently under the hood, right? That you don't have to bother about that. So when you do this, it's going to be O of 1. You can implement it yourself, which we will see today.
So under the hood, like what's data
Yeah.
structure is
Another,
saying?
you can use a linked list. A linked list is really powerful, actually. We will see it later. I mean, let's say we talked about it. Because a linked list using links, what you can do is this. As you have a linked list, right? What you can do is that you can maintain a pointer to this one, right? To this first one. So if you do a pop left, what they can do is that they'll just give you this guy, then they'll move this guy forward here, right? That is constant time. You can use a linked list. It is so powerful, right? Linked list is super. You know, many things, like in databases, for instance, linked lists are so efficiently used. And because linked lists don't expect, contiguous memory like this, they're very powerful. They're super powerful. Yeah. Okay, so that is what I want to talk about today. If you want to use queue in Python, like don't use a list. If you do queue is equal to this thing, it will work. You could work and everything, but note, when you are appending, that's constant time, right? But when you're removing and you do pop 0, it's actually linear time. So have that in mind. So if you really want to use a queue, you have to use deck. And it's a doubly ended queue. If you went through the recordings, you know what a doubly ended queue is. I won't go over it again. Okay. Is there anything else I want to talk about? No. We are beating my time. If after the coding session, there's time, we go over the rest of the things. So now we are going to go over the coding session. And today's one of the questions we solve will actually be design questions because I want you
You
to.
said you go over recursion, actually.
Oh, yeah, recursion. But I can do the recursion today. So what we're going to do is this. The questions we will solve today, we won't do the recursion ones. We're going to have a session to go over recursions, maybe go next week. Because linked lists, we don't really need recursion, but trees are going to need recursion. Heaps are going to need recursion and so on and so forth. We have a recursion video from 2 years ago, which I think was good. I'll share that. But we also go over recursion so people can ask their questions interactively.
Yeah.
So today's questions, we won't go over a recursion question, but we'll go over a design question where we have to implement something using another thing. I'm going to give you a clue to one of the questions we'll be implementing today. One of the design questions, because once we start, there's no pausing. We want to help give people the intuition. So don't forget all these, how to create a queue in Python, how to use a stack in Python, difference between a stack and a queue, the implementation difference, and so on and so forth. Now, one of the questions we'll be solving today, as I said, is going to be a design question, an OOP design. We're going to implement a queue using a stack, right? A queue using a stack. I'm going to give you the intuition. If you've solved it before, you probably know it. But this is going to be the intuition. It's going to be maybe the second question we solve because I want to get people's brain all hyped up. So think of it this way. Assume you have two containers, right? I hope everybody knows what a stack and what a queue is by now. If I say a queue, consider joining a line, right? Like in Opoku School Dining Hall, we really respect order. So if you came first, you enter the door first. If you came second, you enter the door second. If you came third, you enter the door third. That's what a queue is. A stack is different. A stack, if you came first, we don't care about you. If you came second, we don't care about you. If you came third, we don't care about you. A stack is when a vampire is attacking us. They attack this guy first, that's a stack. Then they attack this guy second. Then they attack this guy third. That's how it's like. So those are the differences. For a stack, the last guy will be kidnapped. The last guy will be consumed. The last guy will be devoured. For a queue, you'll be saved first. So that's basically the difference. So just look at this picture. So if you want to implement a queue using a stack, you can also do the reverse, right? This is the intuition. Look at the intuition. It's so pretty. Look at this intuition. We start. When I want to add an item, so this we're going to call this stack 1. So these are stacks. We want to implement a queue, right? We want to implement a queue data structure. So this is going to be the intuition. This is the algorithm. You're going to have two stacks, stacks 1 and stack 2. The first item you have, add it to your stack 1. When you get something for now, add it to your stack 1. Something comes, add it to your stack 1. Something comes again, add it to your stack 2. Let's call this first item we added A, this B, this C, right? Note we are trying to implement a queue. That means that whenever I call this my data structure, let's call it D, whenever I'm like, get me an item in D, it should return to me, it should function as if it's a queue, right? That's what it should be in your mind. So when I say, give me the first item in D, give me an item in D, what item should it return? Is it A, B, or C? Note, D is a queue. This is just implementation details, right?
Should return A.
You should return A. Are we all convinced? Like, you have added items to your stack, right? You have your D. Your D is a queue. Let's call it queue. You have your D queue. And you do queue dots. Let's say add an item. Queue dots add an item. Queue dots add an item. Right? You first added A, then you added B, then you added C. And under the hood, this is how we are implementing it, right? Now when I say get me an item in queue, it should return to me A, because that's how a queue works. The first item that was added is the first item that should be returned, right? Okay. So let's move on. Let's see how we can do this. Now we know for adding, we can just add it to the one container. See, the intuition is very basic. You just follow me carefully. See, one line definition of the intuition is this. Imagine you have two cups, right? No, if you get a cup back more, or you pour the items into one cup. If you want to see the other one, right? If you want to see the item that is at the bottom, what do? You empty it inside this one, right? If I empty this inside this one, look at this. If I empty this inside this one, what happens? I don't want to give you everything because you'll be solving the question. If I empty everything inside this one, what happens? The C will come to the
It
bottom.
will be reversed. Yeah.
Exactly. It will be reversed, and then the A will come, right? Then, so if I want to, if they ask me to get, the first item on the stack, all I have to do is I have to then pop from the stack 2, and then the A will be returned, right? So that is basically how it's going to work. So if you want to implement a queue using 2 stacks, this is the intuition. Have 2 stacks. If you want to append, always append into 1 stack. If you want to pick, right, if you want to remove something from the stack, empty that 1 stack into the second stack, and then all the items will end up being reversed. Then the guy you need will come right at the top. You just return that guy, and that is it. Someone will be like, is this really constant time? Well, the appending is constant time, but then the popping, when I'm removing, is it really constant time? When I'm removing, is it constant time?
When you're removing from the stack or like.
Yeah, so when I'm removing, so you realize that when I'm just, after I have poured everything from stack 1
Yeah,
over
if you're popping from the second stack, it's constant time.
when you're indeed popping from the second stack, it's constant time, but you do some extra work before you pop it. What is extra work? You transfer, like you move the items in this stack 1 into stack 2. Is that constant time?
No.
That's not constant time, right? It's not really constant
Yeah,
time because
linear
you're
time.
pouring. After you pour and you're just removing the A, that's constant. But when you're pouring, the time is proportional to the length of whatever you're pouring, transferring from stack 1, right? Do you agree with that?
Yeah.
Yeah.
Good, but there's something called amortization. Amortization is this. Amortization simply means this. Sometimes in life, forget life. Sometimes let's say eating. Ghanaian eating. When I was in Ghana, so I mean I do it. When you're eating the food, when you're eating the rice, sometimes the whole rice is like this, and the meat is small here like this. But we eat, and then some of us, last minute, the last morsel, we consume that with the whole meat, right? Then to us, we feel satisfied. We feel like that last consumption can spread over the satisfaction over the whole bowl, right? That is how some people eat. Some people don't eat that way. Some people too, what they do is that every little rice they tear, they add some small meat. Every little rice, they add some small meat. Any little rice, they add some small meat. So in effect, we are all satisfied, right? That is actually how this thing is working. What is working is this. This thing we just did, where we do some massive work, right? At some point, we only do it like once, right? We only do it very few times. We want to pop, right? That is when we do that work. And even that work, it's not even like always done, right? Sometimes we may even transfer just a few items. It's like this second scenario here, where you don't, you eat the rice raw without the meat. Then at some point, you're like, okay, I'm getting to the end, let me add some meat, and so on. But in fact, right, it spreads, but in effect, it's like doing it this way, like spreading the meat across it. So it's a multi take where some massive work is done, then you spread it across everything. So in effect, scientists will tell you it is constant time. It's actually constant time. You see this in other data structures, especially even red black trees. You can see stuff like this. So it's actually constant time in effect. Plus, you may even make fewer calls to the pop method. We can look into these amortization and other things gone later in future, but it's actually constant time. Okay, let's go to the coding. We've talked a lot for 30 minutes for all these. Yeah. Now to the fun part. Is everybody ready? Okay, I'm giving you 30 seconds break. 30 seconds break. Everybody should relax, they should chill. We're about doing the coding part. I know some people are excited for that. They're here for that. Let me also set my things up. Screens. This is screen two. Okay. Are we ready? I need extra 30
Yeah.
seconds. Okay, can you see my screen? Yeah, yeah.
Yes, we are looking for Yam Seattle.
Oh, ha. Actually, okay. So what happened was, I came across this video yesterday. It was boiled yam with some classic stew with everything. And I'm like, ah, should have been in Ghana, should have been home. But nah, it didn't happen. It didn't happen. Yeah. So what we're going to do is this. Oh, right. And because we want to show the question that we are solving in some time frame, we are going to have open the question to the side too. Just so when we post the recording, they know the question we are solving. And this thing wants to take the full screen off. Okay, I know what to do. It's not as if we need the full. Oh, sorry, give me a second. Okay. Okay, so the questions for today. Wait, is everybody ready? Hey, I
Yeah.
can't. Are you people ready? Oh, we should take a break today.
Yeah.
Okay, I actually have the questions already open here. Okay, so the first question, we start small. And because people are now warming up and stuff, we're gonna make this. Let's reset here. Okay. Okay. This is the easiest question we will have. So please, let's do it quickly. And I'm gonna even give you more time to solve this question. Where's chat? Okay. So our first question. Wait, sorry, I can't find my chat. Give me a second. Okay, I can find it now. So this is the first question. Um, I've sent to the chat, and it's 5 minutes. Please start. If you've already solved it, please reset it quickly and write the code from scratch.
Mm.
Okay, the next one is relatively simpler. If you didn't finish this, it's also 5 minutes. And once you sum up the time for the first one, that's on you. But make sure you finish this one. The next one is in the chat. It's valid parenthesis. I'll suggest you finish valid parenthesis first and then come back to this, but it depends on you. Okay, next one. I want to take a break. Okay, let's take a minute break. A minute break. We have two more to go. A minute break. Hey, are people still alive on the call?
Yeah, we are here.
Okay.
We do, boss.
A minute break. Let me resume. Okay, minute is up. Next is asteroid collision. Also 5 minutes. And then the last one here, simplified path, also 5 minutes. Okay. Yep. And so we are done. I was actually beaten by time. Um, let's see. Wait, is everyone done? Or we should give a 1 minute bonus to ourselves. What do people think? Let's collude. Should we collude?
I don't think like 1 minute to do anything.
Okay, okay. Let's give 5 minutes for everybody to make touches on whatever they have to make touches on. 5 minutes. Do we all agree?
Yeah, sure.
Okay. Okay, I think we've got enough time. And yeah, and we are done. Okay, so what's the time now? We are 13 minutes in. So I want us to go over the questions and see which ones we found difficulty with. But in the same vein, I also know we are behind on time. So I'm going to ask, could anyone finish all the stack questions? Because I know I intentionally took some from below the list. Could anyone finish all the stack questions? Not really, right? Let's see the chat. Okay, sorry. Oh, okay, yeah, some finished. Okay, good. So this is what we're going to do. I know some people couldn't finish. Wait, had everyone solved simplified path and asteroid collision? Okay, okay, good stuff, good stuff. Okay, so I know some people had difficulties with this, so this we're going to do on this week. We've gone this week. We're going to do 2 pointers. We're going to do 2 pointers and stacks, queues, and decks again. So for practice, please finish. Let me send it. Oh, you're not even seeing my screen. Sorry, give me a second. Share screen, desktop one. Can you see my screen? The one with neat code?
Yeah.
Yeah.
Okay, so this is what we're doing on this week. This week, needs code 150, finish 2 pointers. All the easy and the medium. 2 pointers, easy, medium. Please finish everything. Finish everything. And finish the stacks questions you didn't finish here. Just 21. Omit the hard, ignore the hards. Do this. So this week we are doing 2 pointers and stacks. Please finish these. Finish all the questions here. I don't know if people don't know, but there are solutions here, right? Like you saw why apparently it doesn't make sense to you. You just open this. I tell people if you have to
Hey
watch this
everyone,
video,
welcome.
if you have to watch this video 20 times, watch it 20 times. Like it doesn't matter. I wish I like see watch it 4 billion times if you have to. Now, if this one doesn't make if the video doesn't make sense to you, you come here, you go to solutions, people who are bored and have no life, post their solutions here too. You open here, you create sort by. So this thing, sort by most votes. I usually choose that. If people trust them, I trust them too. Then this guy says he has a Python one. And be careful, some people write very silly solution. They write like one-line solution. Don't do that. Write solution from a guy who puts in effort. He creates a dictionary and everything. So you read this, it doesn't make sense to you. There's even ChatGPT now. I prefer Meta AI though. Open your new tab, go to meta.ai. Very, very easy peasy. You come here, you ask the guy, copy the code. What is it? Copy the code as the guy. What is this guy doing? They've definitely trained this guy on lead code, so he can give you something. And yeah, there you go. So please, if you want to watch the video 20 times, watch the video 20 times till you understand it. So this week again, complete the stacks questions, but that is underneath code all. Stacks is underneath code all. Don't forget. I'll send it to the group again. 2 pointers is underneath code 150. I'll send some what do you call it? Resource on 2 pointers. You already have the stats resource in case you want to refresh your mind on stats. One thing that helped me to learn 2 pointers was this website. Even them, it's not like they really taught it, I would say. It was more like the practice things, but I think it helped me develop the intuition. Let's see. I bought their course one day. I guess we probably have to buy it. It's so expensive. These people, scammers. Actually, they're not scammers. Actually, no. We can use the Design Gurus. I think the Design Gurus website. Okay, we probably have to buy this particular bit. Grokken. Give me a second. I think when to buy this one is for life. Oh, okay. Lifetime is $100. How many plots of land can it buy in Ghana? 0. Okay. Yeah. So I think that was like 2, 3 years ago when I was learning. I actually used it wasn't on this same website, but they introduced usually. Actually, these ones are free. Oh, good stuff. See, let's do this. Yeah, on educative, it's the same course a modified website they've actually brought to educative. Educative, you have to pay. Yeah, but at that time I was desperate to learn stuff, so I starved myself for 2 weeks, no food, no water, and then bought this. Let's see. Yeah, exactly right. You see here it's like locked, right? And stuff. But the people who created it, their sites, you can watch it for free. Okay. So you're going to use this one then. Yes. So we're doing 2 points this way. I'll send that link actually. So you finish this and they kind of like take you through questions that help you develop the intuition. And I think it helped when I started because like my whole brain was like 2 pointers for like a couple of days, right? They take you through 2 pointers, then fast and slow pointers, and so on. So that's what we're going to do. Let me see if the free ones are enough. If not, we will just buy the premium one and then share it. So let's see. Let's see. This is good. This is good. This is good. 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 Let's see the hard locked ones. Don't worry, this question is only is good. We don't need it. Uh, oh, this question is only good. We don't need it. To be honest, I think the free should work. If you don't agree with me, see you in my chambers. Uh, okay, so we're doing gone this week. I'll send the link. We're doing the 2 pointers pattern. Yeah, I'll send the link. All the free ones. Kill all the free ones. Once you're done with all the free ones, don't worry with fast and slow yet. You see fast and slow when you do linked list. Forget nobody should do fast and slow unless you want more challenge. But these are just linked list questions. And this is something I'll actually teach. They're like easier ways to think about these things actually. So gone this week, we're doing 2 pointers. And I'll have a brief overview of it though when we meet gone next week. So this week, finish your stacks if you couldn't finish them from last week. We already sent the resources. Then go to 2 pointers. The questions you saw on the 2 pointers here, these questions are also like kind of the same one Design Guru has here. Some if you even solve two sum, this is just two sum, right? And so on and so forth. Okay, if you couldn't solve any questions you struggled today, this is a time for you to confess to yourself and confess to whoever you have to confess to. Sit down, go on after this, go through the materials again, solve the questions again. That has to be second nature to you. Some of the questions will adjust to 7 minutes from God willing next week. Because I think some people, their typing is one thing, and some people to retrieving information is another thing. Some of you is merged together, so you need less time. So we'll do that God willing next week. If you haven't started practicing, please do. Assume you have not been diligent with us. It's been 2 weeks, you probably lost so much. So if I were you, I'd start. We are posting the recording, so go through that similarly. And yeah, Eric's session, the session Eric started on God willing Wednesdays to go through questions. So you see, we do a few questions. Eric's session, they actually go through more, and they actually go through questions you've probably not seen, but it's the same concept you are learning. If you can join, definitely join.